Hi, everyone. So I'm Nick Solomon from Data Camp. I recently graduated Reed College in the class of 2017, and hopefully you can all see my screen now. So I'm going to be talking about local dependence in exponential random graph models. This was a project I worked on for my senior thesis at Reed, and I managed to prove a few theorems about these new models. So let's dive right in. So first off, we're going to start with random graphs. And what is a graph? Well, a graph is a picture like you see here, is a set of edges and vertices, and each edge is a pair of vertices. So we can say the edge E is equal to the pair ij for ij in V. And you can also represent a graph as an adjacency matrix. So this is basically an n by n matrix for a graph with n vertices, where the ijth entry is 1 if the edge ij is in the edge set capital E and 0 otherwise. The adjacency matrix is the most useful form of representation for the work I did. So that's how I'll be thinking about graphs throughout this talk. A random graph is just a graph where you take each entry of the adjacency matrix and consider it as a random variable. So now that your graph is all of a sudden stochastic as opposed to being fixed. And you can also add vertex attributes. So this says each vertex in the graph maybe represents a person, and that person will have an age or a gender or some group that they're a part of. And you can add these fixed attributes to the graph for when you're modeling it. So an exponential random graph model is a class of model that already exists. You're going to hear me call them ERGMs. Funnily enough, that's actually what people call them. So an ERGM is a broad class of flexible models for random graphs. It takes an exponential form, and it allows the researcher to model network features that are of interest, basically anything you could think of. So commonly people will count the number of triangles in a graph or count the number of edges that are reciprocal. So this looks like this. So you have the exponential of some vector valued function g dotted with a parameter theta over a normalizing constant. That normalizing constant is particularly important. If you take a look at that function c of script y theta, you'll see that it's a sum over all y in y, where script y is actually the support of the random variable. So that's going to be all the possible random graphs in our sample space of that e to the g of y dotted with theta. So this quickly becomes actually impossible to calculate. This is a completely intractable normalizing constant because of the huge number of possible random graphs. So even for, say we have 10 vertices, which is a very small number in most applications, the number of graphs on 10 vertices is something like 2 to the 45, unless I'm mistaken, which is a huge number. So a random network is a variation on a random graph. Basically, all we've done is added vertex attributes that are now random variables. So as opposed to having fixed vertex attributes, we're actually considering these now as random quantities that vary based on perhaps based on other quantities of based on features of the network, or maybe the random variables will have dependence with the features of the network. So it really allows for more flexible models in where you want to consider the attributes of the vertices as being non-fixed. So to more formally define this, take y to be a random graph and take x to be a random matrix of vertex attributes. So say you have n vertices with p attributes, x would be an n by p matrix, and each entry would represent a different random variable. And then we would say that the exponential random network model is given by this equation. So it looks very similar to the exponential random graph model, but you'll see now the explicit dependence of the vector valued function g on the vertex attributes x. And it has a very similarly nasty normalizing constant. So now, as opposed to being a sum over all possible random graphs, it's going to be a double integral over the Cartesian product of the sample space of graphs with the sample space of the random matrix x. And it's just at this point, it's completely impossible to calculate. It's impossible to even think about. So now onto the good stuff. So I was able to prove two theorems. The first theorem is that locally dependent sparse exponential random network models have strongly consistent maximum likelihood estimates. So I'll get into what I mean specifically by locally dependent and sparse, but basically this means that as you try to do maximum likelihood estimation with your random network models, that you can be sure that you're actually converging towards some true parameter value that does exist. And the second theorem is that these same models also have asymptotically normal statistics. So what I mean by this is that as you grow the network, statistics of the graph. So for example, the proportion of people with a certain attribute or the number of triangles in a graph, these become normally distributed as the networks grow larger. So if you imagine resampling a network with 200 vertices, if you're able to draw 1,000 networks with 200 vertices each and count the number of triangles in each one, you would get a roughly normal distribution, and that would get better and better as the number of vertices in the network grew larger and larger. And of course, this only applies to certain classes of statistics because the number of functions that you could have from a random graph into the real numbers is, there's a lot of them. But these statistics cover most of the use cases in practice. So to define local dependence, this definition, I wouldn't try to read through it. Basically, all it's saying is that we're able to partition the network into a set of neighborhoods. So we can basically say there are clumps in the network, and then within these clumps, the edges are allowed to be dependent on one another, and outside of these clumps, the existence of edges is forced to be independent. And we're able to factor the probability measure on the network into a certain form because of this dependent structure that we're assuming exists. Basically, all it's saying is only your friends matter. If you think of a social network in terms of a friendship network. And sparsity basically says, is just some condition on how quickly the edges between nodes that are in separate neighborhoods grow as the network grows larger. So basically all this is saying is that we're converging in the limit to some fixed number of edges between neighborhoods, which is to say most of your friends are in your neighborhood. So this is saying that these theorems only apply for graphs in which there are clumps and which the clumps are relatively well defined. And sociologists and researchers in the social sciences have found this to be true enough in practice for these to be reasonable assumptions to make. So to prove the existence and consistency of maximum likelihood estimators, basically all there is to it is to show that we can recover the distribution of a subnetwork from the larger network. So if I have a network with 200 vertices and I extract a subnetwork with, and I subtract a subnetwork with 20 vertices, I'm able to recover the distribution of the subnetwork from the 200 vertex network by marginalizing with respect to all the vertices that were not extracted. And this means that these form what's called a projective exponential family. It's not important to know exactly what that is, but it follows from a result that was proven by Schlese and Rinaldo in 2013, and there should be a citation there. I apologize for that. So to prove asymptotic normality of statistics, this is a little bit more involved. I'm going to go through the sketch of this proof really quickly, but basically it starts with dividing the statistics into 3 classes. The first class depends only on the graph Y. The second class depends both on the graph and the vertex attribute, so this depends on Y and X. And the third class depends only on vertex attributes X. So there are further technical conditions on the form of the statistics. Basically, it just has to be a sum of a product of interaction terms, and you have to assume things like 13th moments exist and all sorts of arcane invocations of statistics like that. And there should also be a citation here. I'm not sure why none of my footnotes are showing up, but the first case was proven by Schweinberger and Fellows in 2012. So, but the proofs for 1 and 2 are very, very similar. Really, they only differ in minor technical details. So I'll go through them both at once. So the basic idea is to split the statistic into within and between neighborhood portions, and then we're able to bound the variance of the between neighborhood portion because of the sparsity condition, and it becomes asymptotically negligible. So then we're able to bound the variance of the within neighborhood portion by doing some monkeying around with, covariances and inner products and all that. And then at a certain point, we're able to show that Lyapunov's condition holds for the within neighborhood portion. And then the result follows from the Lindbergh-Feller central limit theorem, which shows that the within neighborhood portion of the statistic is normally distributed, and Slutsky's theorem, which shows that the sum of the within and the between neighborhood portions is normally distributed asymptotically because of the asymptotic negligibility of the between neighborhood portion of the statistic. For the third class of statistics, we can order our vertices appropriately to show that a vertex attribute, so for any given vertex attribute, we're able to show that it forms an M-dependent sequence of random variables, where M-dependent just means that each one only depends on the M preceding observed values. So if we order everything neighborhood-wise, say, we can say that for some maximum neighborhood size, every vertex depends only on M or fewer of the preceding vertices. And then the result follows from a central limit theorem for dependent variables that you can find a proof of in Patrick Billingsley's book from 1995. So I was able to do some simulation studies that actually show these. So here's a simulated network. And you can see that as the number of nodes in the network increases, it actually does look like it's becoming normally distributed when you make a density plot of some different statistics. And that is the wrong plot. That should be a normal QQ plot, but that's fine. So I was able to find some standard errors by jackknifing at the neighborhood level, and where the jackknife is just removing one neighborhood, calculating the statistic, and then doing that for each neighborhood, and then doing a calculation with the different values to get an estimate of the standard error. So you can see these estimates are actually pretty close to the true values from a simulation study, which is promising because that means that you might actually be able to do some inference with these. And so further research, software for actually fitting these models, I was not able to get around to writing any software. Standard error estimates could use a lot more work because the jackknife is obviously a suboptimal procedure. Some sort of bootstrap would be much more effective, but it's unclear what it means to bootstrap a network. How do you sample a network with replacement? And so the third class of statistic is only allowed to be a statistic of one attribute because there is no currently that I was able to find multivariate extension of the central limit theorem for M-dependent random variables. So if someone were able to prove that, that would generalize my results even further. And that is all I've got. Are there any questions?
Hi, Nick. Yeah, there is actually one question. The question is, what class or classes at Reed most prepared you for this work?
Yeah, so I was actually most prepared for this work by two classes. So the first class was my mathematical statistics class at 390. So that was the junior level statistics class, the second semester junior year statistics class that covered things like maximum likelihood estimation and the bootstrap and all these kind of theoretical underpinnings of statistics. And the second class that most prepared me was the junior level real analysis class, because that covered things like measure spaces and kind of all this different theoretical machinery that I needed to prove these theorems by working through, what is a probability measure? What does it actually mean that this probability measure has the derivative that gives the density in a certain form, and by going through that course, I was able to approach this from such a theoretical aspect.
Great, Nick. Thank you very much.
Thank you. Thanks for listening. I know this was a whirlwind tour through some complicated math, but you can always you can read the full document in full on my website. So that's nicksolomon.me/thesis, and you should be able to find it. Yeah, and let me know if you have any questions. Feel free to at me on Twitter. There's my Twitter handle down there. Have a great day, everyone. Thanks for listening.